My name is Mike Bordikov. This is a part 2 of the CSS animation guide. In this video, we're going to go over how things are built, as well as take a look at the UDT and the setup tabs. For how things are built, let's go back to the intermediate example and understand how this is functioning and what are the limitations of it. So, I have a few things open here. This is the screen, this is the view I should say, that you see for the intermediate animation, and it has these input values. And the way that it is built is we have arm 1, arm 2, and arm 3. And you'll see that arm 1 has arm 2 inside of it. This is an embedded view, centered where we wanted to rotate. Arm 2 has arm 3 in it, and arm 3 is just itself with the part also present, which we can toggle right here with one of the parameters. And then there's the last robot params that all it really does is adds a base. And looking at the actual logic in here, we have two bindings, one on transform and one on transition. These are pretty simple. They take in the input parameters and they wrap it in some strings, and then you have a functioning animation. And this works great for some applications where you only have one animation that is triggered manually, like so. Now, there are few limitations to this. You can't pause this. So we move it from any angle to a different angle. I can even make the duration longer, and there's nothing I can do right now to stop it short of navigating away from it. But if we wanted to stop, like this one, in a different animation, or even do some other tasks like the Robot 2 is doing, we can't achieve that with just using the regular parameters. What we need is some kind of source of truth. In our case, it's going to be a UDT. That way we can pause it at any angle, and additionally we can convert it from an open loop system to a closed loop system. So right now, once I change the angle, that is when view is gonna get that parameter of 1 second from now, finish the move. Well, the problem when you have two robots is if there's a slight lag between the gateway and you might see glitches in the animation. So to prevent that from happening, we want to convert our system to a closed loop. And to do that, we're going to take a look at the regular robot folder in here. And we have robot 3 open, so let's go in that. So to convert it to a closed loop system, what we have to do is calculate the time and place where we want things to be by. So you can look here and you'll see that this is not saying exactly 1000 milliseconds or 2000 milliseconds. It is fluctuating, and it's about 11 milliseconds behind what the gateway says. And I'm running in Docker, so everything's pretty quick here. You're not going to see a lot of lag, where if you're running from a remote server, you could have a couple seconds lag at times. So most importantly, the UDT, which in this case is the joint UDT, it has this document tag command. And the most important parameter in there is finish by. This is a timestamp in the future that the UDT decided needs to be. This is where the angle needs to be by this timestamp. And you can see it's going to do this transform by this finish by timestamp. And there's a script running on this that will calculate this. If you want to pause it to go over it, be my guest. Okay, so one extra benefit of doing it in one tag rather than two, like we did before in transform and transition, is now we're eliminating race conditions where you could update one before the other. And when you have something that is changing all the time, like you see right here, we go from 2 seconds to 1 second. It really depends which one got to the view first, and sometimes you might have unexpected animations. So by putting it all in one tag, you're eliminating a lot of those. All right, now that we've closed the system, one other thing we need is a state machine, because currently someone would need to sit here and click these to the proper angle all day, every day to achieve something like this. Well, turns out there's an easier way, and it's called a state machine. So let's take a look at how it's built. But first, let's go over the overview of it. So there's interlocks and permissives in the state machine, as well as some actuation, which we're going to talk about a bit later. So interlocks must remain true for motion to continue. So in our case, this allows for pausing of the animation. I'm going to give you an example right here. Once this robot starts moving back, and you can see that my interlocks on the left are not met. It is not running anymore, so it's stopped in place. And the robot too actually had its permissives fail, so it went to a different step. You can see here that for permissives, they must all be true in order for the state machine to move on to the pass step. Otherwise, it will move on to the fail step. So let's bring it to new. I really like this step right here because it perfectly demonstrates what permissives do. So if you look in the bottom right here for permissives, you'll see that sometimes there's going to be 2 of them and sometimes there's going to be 3 of them. And step 3000 only has 2 of them, and it will move on to the step. Well, let's go over to our actual setup, this sneak peek. So step 3000, if the permissives are met, it's going to go over to a step 2190. If they're false, it's going to go over to step 3100. And step 2100 has 3 permissives. It has this extra running check. So because there's a difference in these permissives, we're seeing this animation versus what you saw before where we're just going left to right. Okay. So those are interlocks and permissives. Now, what's actually commanding the motion? For that, we do want to go into the setup. And once we click on one of the steps, we can actually see this is the order things execute: interlocks, tag rights, and then permissives. So tag rights is where the actual motion in our case is occurring. So you can see that it is writing X value, Y value, theta value, and execute XY to the joint UDT. This state machine will actually write to a different UDT. It can actually write to any tag. For the sequence of things, it is outlined right here. So normally you would start a step, you will evaluate the interlocks. If they are good, you will proceed to tag rights. Then you're going to wait for the step duration to complete, and then you will evaluate your permissives. And if the permissives are true, you will proceed to pass step. If not, you will go to the fail step. If you still need more clarification on that, please reference back to the state machine UDT. There's quite a bit of code here. Moving on. So we went over the joint UDT, the state machine, and I think I mentioned the robot animation UDT, which has 3 joints and 1 state machine. All it really does is it wraps all of them together, and it does change some of the tags from memory tags to reference tags. And you can see our animation is going pretty crazy. Let's put it in a happier place. All right. That wraps it up for the UDT page. Let's take a look at the setup. All right, so There's quite a few things in the setup page. And why is it so complex, you might ask? Well, let me show you why it's so complex. And to do that, let me open a second instance. All right. So a lot of complexity comes from the X and Y moves. And normally you can execute things through angles, but in real life scenarios, it's a lot easier to have XY coordinate where you want something to be. In order to achieve that, there is a bit of trigonometry that happens in the background, but what it allows us to do is, if you click on settings right here, you'll see that we actually have some configurable options, and I'm going to change this. As you can see, I did it while it was moving. First animation might be glitchy, but then I will recalculate, and it will continue running even though we just made this limb longer. And let's go ahead and make this one shorter. Again, glitchy for the first move, but then it fixes itself. And we can even go crazy over here and make this something ridiculous, and yet it still aligns. It is best practice to keep arm 1 and arm 2 to be the same length. So let's put that something else. Let's revert this back. If arm 1 and arm 2 are same length, you're going to have least amount of dead zones. So that is why there's so many controls on screen. I hope that clarifies that. And then moving on to what we can actually do on the setup screen. So let me put my robot in manual, and you can see it stop moving. Once you put it in hand or manual, it will just complete its current move. Now, if I click on one of the moves here, you will see that it will go to that location when I command it to. You can also move it using these controls. Moving it in X, moving in Y, and you can even rotate the part. Now you'll notice that it's rotating around center of the part actually. This is different than making the arm 3 rotate, which will rotate around this center, as seen by this. And you can see once I change one, the others also update. We're just going back to a previous step. We don't want to save those changes, but you can actually change these. And let's go back. Let's bring my second screen back. All right, I can scroll on the side. So let me do this first. Okay, so in steps in here, we have tag rates, which will command which XY coordinate we want to go to. And just to show an example, without pausing anything, I can just make sure I hit save over here, and I change step 1990 to 160 now. Let's see what that did. Change my zoom. Now you can see that it was 100 pixels off from where it should have been, which is expected. Let me revert that. And make sure you hit save. And now our animation on the bottom should be fixed. Yep, right there. So you can change these in real time. You don't need to put it in hand. So let's go over ways of programming it. There's, I would say, 3 different ways of doing it. First, you can save the position, then you can save the angle, and then you can use a tag browser right here to do a lot more complex things like showing and hiding parts, controlling anything else. this will write to basically any tag that you wanted to. So you can use this outside of this animation if you need to sync some things. So let's take a look at our first step right here, and let me put it back into hand mode. So right now I have these commanded as XY moves. If I want to convert them to the angle moves, if I re-enter that step, you'll see that will calculate them. I can hit save angles on here, and you will see 4 variables will come over here. In our case, I don't actually want the part, so I'm gonna erase it. And one more thing that came over that you can't see because it's the same value, and take a look here, and duration, once I hit save, you'll see that it goes bold. All bolded values will be changed when you hit save. You normally won't want to do this. You don't want to have X and Y and then angle move. So then you would delete this and delete that, and then you hit save. In my case, I'm not going to do that. I'm just going to restore my previous steps. That is one of the ways. What else you can do is, if you change these values here manually, you can just hit save position, and you'll see that these new values are bolded now. And again, I'm going to restore it. If you actually wanted to take effect, make sure to hit save. As I showed you earlier, you can type in whatever value you want in here also. One of the tricky things is if you do have a Boolean value like this, you do need to type in true. And then to make it false, you can click it again. You do have to double click into the cell first to edit it. That's just the table behavior. So restoring again. And you don't have to just write to these tag rights. You can set up your interlocks through tag browser. And let me find something in here. So on the bottom here, you'll see which tags are selected, and you can even change between which way you want it to be statically addressed or dynamically addressed. So once you have some tags selected here, you can bring them over to any of these tables. You can bring them over to interlocks, tag rights, and permissives. Then you'll want to assign value to them. And then you'll want to hit save. Again, in my case, I'm going to restore, because I don't want to change those. This is very useful for addressing anything outside of the actual robot UDT, because everything on the left side will just be referencing itself, basically. Let's take a look at how the part handling is actually done in here. So there's 2 steps, and you can see that this step is 1 second long and this step is 100 milliseconds long. And one of them turns on the part for robot 1 for itself, and 100 milliseconds later it turns off the part for part 2. And we actually want a slight overlap here, just so you don't have glitchy behavior where you see the part disappear for a split second. And same thing for the drop off. It turns on the robot animation 2 part, and then, I'm sorry, I said turns off. It turns it on here, and it turns off robot 1 part. So this whole time I haven't really been hitting save that much. Let's just show you how this works. Again, so we want to have this value at 65, We hit save. Now if I hit restore, nothing will actually happen because we already saved the 65. And this should have moved our animation to a wrong state. And actually when I go back, because I was messing with the state machine, you'll see that it's in the locked position. If I go back to the setup, I have to put this robot in hand mode, then I can go to almost any other step. Go to this one, and then I can head back to auto, and it will resume running. Okay, and now you'll see that, yep, that's the step that I changed. And let's change that back to 60. Okay, so that is save. It's very important that you save between steps. If I change this to some value and I move away from the step, when I re-enter it, it's already reverted. You can see that the save button also disappears. Restore button is really useful for when you're just playing with things, seeing how things behave. And the clipboard button has a couple special purposes for it. Let's take a look at what I can do. So in a scenario where you have a new step, let's make something right here, you'll see that it has 0 interlocks, 0 tag rights, 0 permissives. What we can do is click in here and we can go do manipulation on steps, interlocks, tag rights, and permissives. In my case, I am going to go into interlocks. I'm going to propagate interlocks. Now when I click that and I enter the step, now you'll see that I actually have 2 interlocks without ever typing them in. That's just because I'm copying them. It's very common practice to have same interlocks for every single step. Your tag rights and permissives are normally different. So that's one of the functions with interlocks. We can also do the same thing for tag rights. Let's copy them. And you'll see that my clipboard lights up. And we have values in here. This is just an array of a JSON. And we can take this and we can put this in Notepad++. Any of your text editors do replace all on this. And we can paste it back in. And just as an example, I'm going to change these values a little bit. We'll go 45, 61, or 66. And I'm going to update. Then when I come to my new step, I can paste these. And over tag rights, paste tag rights. And you can see these are the values that came over. So this is really powerful for doing changes to multiple steps at the same time. And you can do the same things with interlocks, tag rights, and permissives. All of these behave the same. So one other reason to use this is you can actually back up entire steps. And you will see that this has everything, all of the interlocks and permissives for every single step. You can back it up using this tool, or you can simply go in here and export your tags. That about wraps it up for this demo. Thank you very much.